Hey guys, today is the last day I will be studying. Today I will complete this last memory management unit topic from OS, and Uh, I will start SQL. I mean DBMS. Okay, let's begin. Memory management techniques, contiguous memory allocation. In multi-programming environment, we have multiple processes in the memory to keep the CPU utilization high. Okay, and to make computer responsive to the users. Okay, to realize this increase in performance, however, we must keep several processes in the memory. That is, we must share the main memory. As a result, we must manage main memory for all the different purposes, chip processes. Logical versus physical address space. The logical address space is generated by the CPU based on the size of the process which is running. Uh, the logical address is basically the address of an instruction or data used by a process. User can access logical users can access logical address of the process. Users has indirect okay, we can't directly access physical address, but we can access physical address through logical addresses. Logical address does not exist physically, hence a virtual address. Logical address is also known as virtual address. The set of all logical addresses that are generated by any program like the set of all logical addresses that are generated by any program referred to as logical address space. How can a program creates multiple logical addresses? I want to know that. Can me, but this is also in non-contiguous allocation also, right? So when we divide so even when we divide the process, like that means when we do do pages of different sizes, then also that is a single logical address, right? Then what does this the set of all logical address that are generated by any program is referred to as logical address space? What does this mean? Mhm. Okay, I have to so I want to know more about this array in JC. Okay, 0 to max physical address, an address loaded into the memory address register of the okay, what does physical address means? The actual um, place where the process data is stored or process is loaded. The actual physical address is the actual address where the process is loaded. An address loaded into the memory address registered at the physical memory. User can never access the physical address of the program. I got diverted between. User can never access the physical address of the program. The physical address is the memory unit. The physical address is in the memory unit. It's a location in the memory. It's a location in the main memory physically. The physical address can be accessed by a user indirectly but not directly. The set of all physical addresses corresponding to the. Okay, this is fine because all physical addresses are not in order, so the set of all physical addresses corresponding to logical address is commonly known as physical address space. Okay, the set of all physical addresses correspond. Okay, this is fine because the set of all logical addresses that are generated by any program. Logical address space, because every process has different logical address space. The set of physical addresses. Set of physical addresses corresponding to logical address, because why we are saying set of logical addresses, because the logical uh, the physical addresses corresponding to logical addresses are not contiguous. So the logical addresses are contiguous, like 0 to max, but these, when we map these logical addresses in the memory, so those are not in contiguous way. So in the contiguous memory allocation, these physical addresses are also contiguous are also contiguous. It is computed by the memory management unit. Okay. The logical address to physical address translation is done by memory management unit. So the range of physical address is base from base plus max. The runtime mapping from virtual to physical address is done by a hardware device called the memory management unit. Okay, the memory management unit converts virtual address into physical address in the runtime. The user's program mainly generates the logical unit. The, the user's program mainly generates the logical address, and the user thinks that the program is running in its logical address, but the users will have the illusion of working on the logical address, but the program mainly is but the program actually is running in the physical address. Okay, what the user think is we are dealing with these logical address spaces. Our data is stored in these logical address spaces, uh, but this data is actually stored in the physical memory. That these logical addresses are only mm, these logical addresses are generated only to ensure that a process doesn't access another process memory, to provide security and protection for other process memory. Okay, logical address is mainly due to provide security and protection and isolation for other process memory. So each process has its own logical address. How does OS manage the isolation and protection? OS provides this virtual address space concept. Okay, okay. Isolation and protection of memory is done with the help of virtual address space concept. To separate memory space, we need the ability to determine the range of legal addresses To separate memory space, we need the ability to determine the range of legal addresses. Determine the range of legal addresses that the process may access, and to ensure that the process can access only these legal addresses. The relocation register contains the value of smallest physical address, base address. Relocation register contains value of the base, the limit register and the relocation register. So memory management unit uses relocation register and limiting register to convert virtual address space into physical address space. Each logical address must be less than the limiting register. Okay. Operating system uses various mechanisms to isolate and protect the memory allocated to different processes, ensuring that one cannot access or modify the memory of another process. Ensuring that one cannot access or modify the memory of another process. This isolation is crucial for system stability, security, and preventing accidental corruption. Here are the primary techniques used by the OS to achieve this. Virtual memory. Each process given the illusion that it has its own private memory space. Okay, each process thinks that it is working on its private memory space. The actual physical memory is shared among all processes, but the actual physical memory is shared among all the processes. But the OS maps virtual address to physical address. Memory management unit maps virtual address to physical address, allowing processes to operate as if they have their own dedicated memory. Memory management units maps the logical address dynamically by adding the value in the relocation register. When CPU schedulers select a process for execution, the dispatcher loads the relocation and limiting register with the correct values. Okay, there will be a so initially this relocation register and limiting register contains the previous process. When the CPU scheduler selects another process, the dispatcher loads these with the current values as the part of context switching. Since every address generated by the CPU is checked against these registers, we can protect both OS and other user programs and data from being modified by the running process. Okay. Uh, Any attempt by a program executing in user mode to access the OS memory or other users. So whenever we try to the memory of other process, it will error will be thrown. By the allocation method or allocation method on physical memory. Contiguous allocation, non-contiguous allocation. Contiguous memory allocation. In this scheme, each process contained in a single contiguous block of memory, fixed partitioning. The main memory is divided into partitions of equal sizes. Okay, fixed partitioning అయిందనుకో. Okay, then there will be internal. Okay, fixed partitioning in internal leads to internal fragmentation and external fragmentation also. If the size of the process is less than the total size of the partition, then some part of the partition gets wasted and remain unused. This wastage of the memory is called internal fragmentation. External fragmentation. External fragmentation means the total unused space of various parts. Okay, when we do fixed partition, and let's say we have four partitions of size 4 KB, and we have a process. We have three parts of size 3 KB, 4 KB, and 5 KB. We have allocated 3 KB and 4 KB in when onto one partition. In the partition where 3 KB is allocated, there will be 1 KB of space remaining. This is called internal fragmentation. And remain unwasted. This 1 KB is getting wasted and remain unused. This is called internal fragmentation. External fragmentation means, okay, now even though other two partitions of size 4 KB and 4 KB adds up to 8 KB, I can't uh, we can't be able to uh, mm, load the process of size 5 KB into these partitions, since we can allocate max 4 KB process of size 4 KB. Limitation on process size. If the process size is larger than the size of maximum sized partition, then that process can be loaded into the memory. Therefore, a limitation can be imposed on the process size. Fragmentation is the wastage of memory that arises due to the way memory is partitioned and allocated. Fragmentation is waste of memory that arises due to the fragmentation means pieces of memory that is being wasted due, due to the way we are partitioning and allocating the memory. Partition and allocated, leading to use this fragmentation represents the inefficiencies or gaps in memory uses. Low degree of multi-programming in fixed partitioning. The degree of multi-programming is fixed and very less because the size of the partition can be varied according to the size of process. Dynamic partitioning. In this technique, the partition size is not declared initially. In this technique, the partition size is not declared initially. Okay, it is declared at the time of process loading. Okay, dynamic partitioning. So we divide the memory. We partition the memory is divided. Okay, the partition of memory is done based on the size of the process. Okay, what happens due to this? There will be no internal fragmentation, but there will be external fragmentation. Advantages of fixed no limit of size. Okay, and also there is no limit of size of the process. Better degree of multi-programming. Limitation external fragmentation. Making all the free memory contiguous by shifting allocated memory partitions. Compaction or defragmentation. Compaction or defragmentation is making all free space contiguous by moving the allocated address spaces. Making all the free memory contiguous by shifting allocated memory partitions. Compaction is an expensive operation in terms of time and CPU usage because it requires reallocating processes and updating their memory references. Okay, free space management. Dynamic partitioning suffer from external fragmentation. Compaction to minimize the we can do compaction to minimize the probability of external fragmentation. All the free partitions are made contiguous and all the loaded partitions are brought together. By applying this technique, we can store the bigger process in the main memory. The free partitions are merged, which can now be allocated according to the needs of new process. This technique is also called defragmentation. The efficiency of the system is decreased in case of compaction. Okay, efficiency of the system is decreased in case of compaction, since compaction is a time consuming process because we have to change the address space of every process. It requires reallocating processes and updating them. Okay, we have to reallocate the process to the new address spaces and update their memory references. How free space is stored or represented in OS? It is represented with the linked data structure. Free holes in the memory are represented by a free list. How to satisfy a request? Okay, now n size from a list of free holes. Various algorithms. Okay, now we have to allocate a process. Now we have a list of free memories, like free holes of memory of size of various sizes. Now how can we allocate a process? How can we allocate memory to a process which is being loaded in the memory? How to allocate memory to the process? Now we can do what we can do is we iterate over the free list, and whenever the size of that node becomes larger than the size of the process, then we can allocate it there. Then at that time we allocate the process. We allocate the memory for the process in that free list, in that hole. We keep the process in that hole. Mm, that is called first fit. And now comes the next fit. Now we should now whenever we want to allocate the memory for the new process, we don't iterate from start again. We iterate from the current node where we have allocated allocated memory previously, and again we iterate from there, and we allocate a hole which is large enough to allocate this process. Now the worst fit and the best fit. The worst fit says allocate the largest hole which can allocate the process. Okay, keep this process in the largest hole available. Best fit means keep this process, allocate memory. Okay, keep this process in the smallest hole which can accommodate this process. Due to first fit, it takes time. Okay, so simple and easy to implement fast. Next fit enhancement of first fit, but starts searches always from last allocated hole. Last hole that is big enough, lesser internal fragmentation may create many small holes and cause major external fragmentation. Slow as equated hole, free hole list. Allocate the largest hole that is big enough. Slow as equated we use larger hosts that may accommodate other processes. Paging. Okay, now comes non-contiguous memory. Paging means uh, paging means mm, dividing the process into fixed size. The process into fixed size, and also partitioning the memory into fixed size, same size as the size of the process. Okay, we make paging means the process of, okay, okay, how can we say this? Paging means instead of keeping the whole process inside the memory, like contiguous memory, we divide the process into small bits, smaller parts, and we also partition the memory into say similar sized parts. Okay, now the smaller size the small parts of the process are called pages, and the partitions in the memory are called frames. We have to fit these pages in the frames. Now, the main disadvantage of dynamic partitioning is external fragmentation. Can be removed by compaction, but with overhead. We need more dynamic, flexible, optimal mechanism to load processes in the partitions. Idea behind paging. If we have only two small non if we have only two small non-contiguous free holes in the memory, say 1 KB each. If OS want to allocate RAM to a process of 2 KB, memory is 1 KB each. If OS want to allocate RAM memory to a process of 2 KB in contiguous memory allocation, it is not possible, as we must have contiguous memory space or memory space 2 KB. What if we divide the process into 1 KB, 1 KB blocks? Paging. Paging is a memory management scheme that permits the physical address space of a process to be non-contiguous. Uh-huh. Okay, paging, what does paging mean? What does paging mean? A scheme that eliminates the need of contiguous allocation of memory. Okay. Okay, I was thinking paging means paging means uh, making the process into small chunks, dividing the logical address space of a process into smaller smaller pieces. But paging is a memory management scheme. Paging is a memory management scheme which allows the physical address space of a process to be which allows which that permits the physical address space of a process to be non-contiguous. This is where okay what I thought was paging means dividing the logical address space of a process. Making a process uh, dividing the process into smaller blocks. I thought paging means dividing the process into smaller blocks, but what paging actually means uh, it's a paging is a memory management scheme that lets the memory to be that lets the physical address space of the process that lets the physical okay the physical address space of a process to be non-contiguous. Guatemala to be non-contiguous. It avoids external fragmentation. It avoids external fragmentation. The need of compaction. Mm, how it avoids external fragmentation. Mm, mm, mm. No need to compact because there may be internal fragmentation, but there will be no external fragmentation because we can access mm, pages into frames. They are all available. Idea is to divide the physical memory into fixed size blocks called page frames. Okay, the idea is to divide physical memory into fixed size blocks called frames, along with divide logical memory into blocks of same size called pages. Page size is usually determined. Sorry guys, I got distracted. Page size is usually determined by the process architecture. Page size is usually determined by the process architecture. Traditionally, pages in a system had uniform size, such as 4 KB. However, process designs often allow 2 or more, sometimes simultaneous page sizes due to its benefits. Page tables. Page tables. What does page table? Page table stores which frames the page corresponds to. A data structure which stores which page is mapped to which frame, a data structure which stores which page is mapped to which frame. The page table contains the base address. The page table contains the base address of each page in the physical memory. The page table contains, sorry guys, I got, I'm getting distracted too often because I'm thinking about my job. Okay, I will work hard. The page table contains the base address of each page in the physical memory. Okay, every address generated by CPU is divided into two parts. The page number, every logical address is divided into two parts, a page number and a page offset. Page number, let's say some, we will check where this page is loaded in the, is present in the physical address space using in page tables. Uh, Page tables, and we directly add the offsets in where P is used as index into a page table to get base address corresponding to get base address of the corresponding frame in physical memory. Loaded in which frame? Page table is stored in main memory at the time of process creation. Okay, page table is stored in main memory at the time of process creation, and its base page table's base address is stored in process control block. So whenever context switch happens, we don't have to uh, we don't have to uh, restore the total page table. We just have to restore the base address of the page table, and we can do the address translation. A page table base register is present in the system. A page table base register is present in the system that points to the current page table. Changing page table requires only this one register at the time of page table base register. In PCB, only the base address of the page table is stored. So during context switch, we don't have to get the entire page table. We just need to change the base address of the page table in the page table page table base register present in the system. How paging avoids external fragmentation, non-contiguous allocation of pages of the pages of the process is allowed in the random non-contiguous allocation of the pages of the process non-contiguous allocation of the pages. Non Hi guys, I'm getting very distracted, but I'll try to focus. How paging avoids external fragmentation, because we divide the we since the size of frames and pages are same, there will be no external fragmentation. There may be internal fragmentation, non-contiguous allocation of the and also the allocation is non-contiguous. If there are any gaps, we can fill we can fill those gaps. Non-contiguous allocation of the pages or the process is allowed in random free frames of the physical memory. Why paging is slow and how do we make it fast? Why paging is slow and how do we make it fast? There are too many. Okay, paging. Why? Okay, we can add transition look-aside buffer. Why paging is slow? Because there are many pages. There are too many memory references to access the desired location in the physical memory. Uh, Memory references to access the desired location in the physical memory. So first we have to uh, go to page table base register, and we have to go to page table, and in that we have to uh, okay, too many memory references. Okay, um, I don't know how adding transition look aside buffer. Now go to in memory reference and access the physical address, using memory reference. Transition because I look for a hardware support to speed up paging process. It's a hardware cache, high speed memory. Page table is stored in main memory, and because of this, when the memory reference is made, the transition is slow. Main memory. In order to make it more fast, mm, in order to paging more fast, we use transition because I buffer. It's a high speed memory. Mm, Okay, transition because I buffer is a hard to add support to speed up paging process. It's a hardware support to speed up paging process. When we are retrieving physical address, using page table, after getting frame address corresponding to the page number, we put an entry of the into the TLB, so the next time we can get the values from TLB directly without referencing actual page table. Hence, make paging process faster. So if degree of multi-programming, the number of pages process in the memory increases, a degree of multi-programming increases, then each time the process is being context which is happening, we have to flush the TLB. You can also store entries of different processes in TLB by specifying ASID of the process along with page number. TLB contains the mapping of ASID address space identifier is stored in each entry of TLB. Address space identifier. Each process and it is used to provide address space protection. Provide address space protection and allow the TLB to contain entries for different processes. At a time, TLB can contain different process data. When TLB attempts to resolve virtual page number, it ensures that the ACID address space identifier currently process matches the virtual page. It doesn't match the attempt. Is treated as TLB segmentation and non-contiguous memory allocation. In paging, uh, the size of frames are fixed. An important aspect of memory management that becomes unavoidable with paging is separation of user's view of memory from the actual physical memory. Segmentation is memory management that supports the user view of memory. Logical address space is a collection of segments. These segments are based on user view of logical memory. So segmentation is done. Okay. The problem with paging is uh, let's say we have a process containing a function of size 8 KB, and we are dividing into 4 KB and 4 KB. 4 KB into 4 KB. Whenever the function CPU starts executing the function, it needs to change the uh, it needs to access from one frame and has to switch to another frame. This takes a lot of time. In order to make these function to load into the physical address space at the same continuously, we treat it as a segment, and we okay, segmentation. How can we okay, segmentation? The process contains of many segments. So in paging, those segments are equally divided. That may lead to CPU overhead, because when these equally divided pages are loaded into frames, whenever CPU wants to execute a segment, uh, it has to access uh, different memory locations. They are not contiguous. The memory locations which are in which pairs are loaded are not contiguous. This may takes this is some overhead. So if we can load the whole segment at the same time in the main memory, in the physical address. This process is divided into various segments. Paging is closer to the operating system. Paging is closer to the operating system than the user. It divides all the process into the form of pages. All the process can have several relative parts of functions which need to be loaded in the same page. Okay, a process may have several parts of a function which may which need to be loaded in the same page, but due to but it can't happen since the size of a page is fixed. Operating system doesn't care about the user view of the process. It may divide the same function into different pages, and those pages may or may not be loaded at the same time into the memory. It decreases the efficiency of the system. It is better to have segmentation, which divides the process into segments. Instead of dividing the process into pages, we divide the process into segments. What? Because a process may have some parts. A process may have some parts which needs to be loaded in the same page. Each segments contain the same type of functions, such as the main function can be such that the main function can be the total function can be included in one segment, and the library functions can be included in the other segment. Okay, since size of a segment varies, in TLB we store offset along with base, along with uh, the, that segment number. No internal fragmentation. One segment has a contiguous allocation, hence efficient working within segment. The size of segment table is generally less than the size of page table. Okay, the system becomes efficient because same type of functions in one segment. Segmentation keeps same type of functions in one place. Okay, due to segmentation, system becomes more efficient because due to segmentation, same type of functions will be in one segment. External fragmentation may occur. The different size of segments is not good at the time of swapping. Mm, mhm. Modern system, I suppose virtual memory. This is one of the beautiful concept. Okay, let's say we are playing a game. Uh, let's say GTA 6, which hasn't come. Let's say the size of GTA 6 is, let's say, 36 GB, but our devices have a maximum RAM of 16, or let's say 32, but still we can be able to run that GTA 5. How is this possible? So in order to run a process, we don't need entire the entire code. We don't need entire process. We don't need entire code of a process. Entire code of a process. We just need a few. We need some part of a process which are currently being used. A process may contain a process. The size of a process may be large, but the size uh, when we run the process, the size of a frame which is big, which the CPU executes, will be less. Virtual memory is a technique that allows the execution of process Virtual memory is a technique that allows the execution of processes that are not completely in the memory. Okay, guys, again distracted. Okay, I will take a break, guys. I will come again. Not much. 5 minutes break. Okay, what is virtual memory? Demand paging, page faults. Virtual memory is a technique that allows process execution of processes that are not completely in the memory. It provides user an illusion of having a very big main memory. This is done by treating a part. This is done by treating a part of secondary memory as the main memory. Okay, for users, so we feel our RAM is very big. That means it provides user an illusion of having a very big main memory. User an illusion of having a very big main memory. Okay, we think that we have a very big memory. It provides the illusion that it provides user an illusion of having a very big main memory. This is done by treating a part of secondary memory. This is done by treating a part of secondary memory as the main memory. Advantage of this is programs can be larger than physical memory. It is required that instruction must be present in physical memory to be executed, but it limits the size of program to the size of physical memory. So usually we need to keep the instruction in physical memory to execute that process, but due to that the size of a process will be should but it limits the size of the process, so we can't load the process of size which is greater than main memory. In fact, in many cases the entire program is not needed, but in many cases the entire program is not needed at the same time. But in many cases entire program is not needed at the same time. So we somehow want an ability to execute a program, an ability to execute a program that is only partially in memory would give many benefits. So executing a program that is partially in the main memory. So executing a process which is partially in the main memory has many benefits. A program would no longer be constrained by the size of the process can be larger than the physical memory, because uh, because each program could take less physical memory, more programs could be decrease. Since each program takes less physical memory, degree of multi-programming increases, so CPU utilization and throughput also increases. Running a program that is not entirely in memory would benefit both system and the user. Programmer is provided very large virtual memory when only a smaller physical memory is available. Okay, and the size of the program is very large, so virtual address space created by the CPU is also very large. So instead of loading all parts of the program into the main memory, we load the important parts, which we load the main parts of the process in the memory. Demand paging is a popular method of virtual memory management. Okay. Demand paging, the pages of a process which are least used get stored in the pages of the pages of a process which are least used will be stored in the swap space, secondary memory. A page is copied to main memory when its demand is made or page fault occurs. There are page replacement algorithms which are used to determine the page which will be replaced. Rather than swapping the entire process into the memory, we use lazy swapper. A lazy swapper never swaps a page into memory. Okay, medium-term scheduler is used in this short-term scheduler. um, where short-term scheduler is used where long term okay, short term scheduler is used the where short term scheduler and long term scheduler is used. Mm, long term scheduler, job scheduler, chart of scheduler. Job scheduler. Short-term scheduler, CPU scheduler. Ready queue. Lazy swap is used during swapping only when the demand is made. Demand of a page is made. We never we swap the page into the memory. We are viewing a process as a sequence of pages rather than one large contiguous address space. Using the stump swapper is technically incorrect. Swapper pager manipulates entire process. When a process is to be swapped in, the pager when a process is to be swapped in, the pager guesses which pages will be used. At the start, when a process is being loaded into the memory or being swapped in, the pager guesses which pages will be loaded. The pager guesses which pages will be used. Instead of swapping in a whole process, instead of swapping in a whole process, the pager brings only those pages into memory. The pager guesses which pages will be used. Instead of swapping in a whole process, the pager brings only those pages into memory. Thus it avoids reading into memory pages, reading pages that will not be used anyway. Our OS decreases the swap time and the amount of physical memory needed. Valid bit in a page table is used to distinguish between pages that are in memory and that are on the disk. The page say the not valid or is valid but is currently not in the disk. If a process never attempts to access some invalid bit page, the process will be executed successfully without even the need pages present in the swap space. Need of present. Okay. Okay. That's fair. That's what happens if the process tries to access a page that was not brought into memory. If the process tries to access a page which is not in the memory, then a page fault occurs. Access to a page marked invalid. Access to a page marked invalid causes page fault. Paging hardware noticing invalid bit for a demand page will cause a trap. The procedure to handle the page fault. Check the internal table to determine whether the reference was valid or invalid. Memory access. First we check if that is valid or invalid memory access. Not valid, not in the LAS logical address space of the process. Check if check reference the access is valid or invalid. If reference was valid, pager will swap in the page. We find a free frame. Schedule a disk operation to read the desired page into the newly allocated frame. When disk read is completed, we modify the page table that the page is now in memory to read the desired page into the newly allocated frame. Restart the instruction of interrupt the process and access the page through. Page fault occurs. When a process tries to access a page which is not in the main memory, it causes a page fault. The page will swaps in the required page with a swaps the required page if there is a free space, then it will keep that page there. Otherwise it swaps with the page according to a page replacement algorithm. Pure demand page. In extreme case, we can start executing a process with no pages in memory. When OS sets the instruction point to the first instruction of the process, which is not in the memory, the process immediately falls for the page, and the page is bought in. Okay, viewed image page ante. Okay, okay, we we can start executing a process with no pages in the memory. So whenever when which is not approximately okay, whenever we starts executing CPU starts executing the instruction, the process immediately faults, causes phase fault on the page. We use locality of reference to bring out reasonable performance from demand paging. Increased user can run large apps with single physical memory. Disadvantage of vertical memory. Page replacement algorithm. Belady's anomaly. Okay. Anomaly means the number of in general, as number of frames increases, number of page faults decreases. But the but this is not always the case. There may be cases when even when even when these things number of frames there are there may be cases such that even though number of frames increases, the page faults also increases. When page fault occurs, when the process tries to access a page which is not in the main memory, process try to access a page which is not currently present in a frame, and OS must bring the page from swap space to a frame. OS must do a page replacement to accommodate new page into a free frame. Page replacement to accommodate new page into free frame. But there might be possibly the system possibility that the system is working in high utilization and all the frames are busy. In that case, OS page replacement to accommodate new page. And all the frames are busy. In that case, OS must replace one of the pages allocated into some memory page to be replaced. Some allocated page new page swap into the free frame types of the okay the aim of the comes the main aim of page replacement algorithm is to minimize number of page faults because causes some overhead, no useful work. It does page faults. Okay, first in first out. Optimal page with first in, first out. Ballad is one first in, first out. Replacing the oldest page. In this page replacement algorithm, we will replace the oldest page which you what you're referring to. By replacing the oldest page, is it implement performance? Not always good. Number of frames. Okay. In general, with any page replacement algorithm, as number of frames increases, page fast decreases. But in first out page replacement algorithm, the number of there are cases where number of page fault increases with the number of frames. Is that different? Find a page that is never referenced in future. Optimal page replacement algorithm is find a page which is never replaced in the future. If exists, then swap. Then replace this page with new page. If there is no such page, find a page. Find a page that is referenced farthest in future. Find a page which is referenced farthest in the future. Replace this page fault rate on difficulty task requires future knowledge of reference streams. Future knowledge, like which page will come farthest in the future. Recently we can use recent past as an approximation of the near future. Then we can replace the page that has not been used for the longest period, like least recently used counting. Frequently used. Buffering means storing data, special process of temporarily storing a data in buffer before it is transferred to its final destination. Spooling means a technique used to manage output devices. Spool the output from a program is stored in a special area. Okay, spooling is used to devices to manage output devices. So, the spool access the following program access buffer. Spooling the output from a program. Output from the program is stored. Spooling is a technique used to manage output devices. The output of a program is stored in the spool. When spooling, the spool acts as a buffer. crashing. If the process doesn't have the number of frames it need to support pages in active use, it will quickly page fault. If the process doesn't have the number of frames it need to support pages, if a process doesn't have the number of frames it need to support pages in active use, it will quickly page fault. At this point, it must replace some page. However, since all its pages are in active use, it must replace a page that will be needed again right away. Consequently, it quickly faults again and again and again, replacing pages that it must this high paging activity is called crashing. When we don't have enough we don't have enough number of frames to allocate the number of frames to support pages in active use. Okay, let's say we have 4 classes. System is crashing which spends more time serving reviews logs than security process. This model is based on concept of the locality model. The basic principle states that if we allocate enough frames to process to accommodate its current locality, but whenever it moves to some new locality, but if the allocated frames are less than the size of the current locality, the process is bound to crash. Okay. Whenever we load across, we keep the process into memory, we keep pages if we allocate enough number of frames to a process to its current locality. So we have to allocate enough number of frames to a process to accommodate its current locality. So we have to allocate enough number of frames to a process to allocate its current locality, to accommodate its current locality. So page was only occurs to handle this, we have to allocate enough number of frames to a process to accommodate its current locality. Means let's say you are playing PUBG game, so we have to allocate. Uh, we should we 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 definitely need pages. It contains the code up to a range up to 500-meter range we can visible in the screen. After that we don't need those pages, but this current locality, what are the pages which stores the current locality, we definitely need those pages. If there are uh, if the allocated frames are less than the current less than the size of the if the allocated frames are less than the size of the current locality, mm, size of the locality, it is bound to crash. Page fault frequency. Thrashing has a high page fault rate. We want to control the page fault. When it is too high, the process needs more frames. Conversely, if the page fault rate is too low, then the process may have too many frames. We establish upper and lower bounds on desired page fault rate. If page fault rate exceeds the upper limit, allocate the process another frame. If page fault rate falls below the lower limit, remove a frame from the process. By controlling page fault rate, thrashing can be prevented. Okay, that's it, guys. That's it for today. Okay, I want to know where these are like schedulers. Okay, this one. Okay, ready Q2. Here what is said. Ready Q2 CPU. Most progress QQ's scheduler. Long-term scheduler is a job scheduler at the entry point where it is used. At the entry point of the system, deciding which job to admit from the job pool on this. It is used at the entry point of the system, deciding which job to admit from the job queue. Job queue to ready queue. Ready queue to CPU. Job queue to ready queue. వచ్చేసి లాంగ్ టర్మ్ షెడ్యూలర్. రెడీ క్యూ టు CPU వచ్చేసి short term scheduler. Decide the CPU. Deciding ready queue. Short term scheduler decides which process is ready, which process in ready queue gets the CPU next. Middle term scheduler. If the system is overloaded, middle term scheduler may start working. overloaded. Middleton scheduler is used when the system is overloaded. The system is overloaded. The memory is overloaded with many processes. Medium scheduler may swap out a low priority process to disk temporarily and later resumes it. Okay, short-term scheduler decides which process in the ready queue gets the CPU. Short-term scheduler decides which job to update from the job queue to main memory or the ready queue. That's it, guys. This is for today. Bye bye.